Okay, quick tutorial on how to generate ADC from diffusion datasets. So let's say that you want to do analysis on ADC, so apparent diffusion coefficients, but you don't have, so usually the scanner would generate an ADC map just like this that you can use directly. But sometimes for some reasons the scanner does not generate it, so you're left alone. You have to generate your own. So if it doesn't generate it, usually it outputs a diffusion dataset that usually looks like this. So when you try to open it, I'm using ITK Snap just because it's convenient. It's not necessary, but you can use another DICOM viewer. It has 3 volumes. So usually one is a B0, so T2, purely T2 weighted image. One is a trace and one is, I don't know. We'll see. We'll see soon. So this is probably a trace, the way it looks. So, oh, it's to be values. This is what it is. Looks like a B500, but it doesn't matter. Um, so to start, what I'm about to do, you would need DICOM to NII, which converts DICOMs into Nifty format. The computer on this lab already have that, and you would need FSL. So you can don't if you don't have them, you can download them for free online. Um, so let's, so the first thing to do is open a terminal. All computers have a terminal, in case you don't know. I don't know where it opened it, but yeah, here it is. And it looks like this. So with the terminal, you cd change directory where your DICOMs of the diffusion dataset is. To make sure you're there, you can also ls. It lists all of the files that it finds. So these are in DICOM. We have to convert them into Nifty formats in order to work with them. As I said, I already have installed DICOM to Nifty, so DCM to NII, depending on your version, what version you have. You may have to use DCM to NII, or what I have is DCM to NII-X. And then you can just give as an input the name of any of a specific, just one of the DICOMs that you have. So you can do this, DCM to NII-X, and then you paste the name of the one of the DICOMs. It's going to convert all of the DICOMs into Nifties, while DICOMs are stored in a way for which each slice is a different file. Nifties are stored in a way for which all of the images are compressed, are not compressed is not the right word, are included in the same Nifty. You will see that this DICOM to NII conversion has generated an .NII file which contains the images. First of all, we don't work with .NII as it is. We compress it into NII.gz. To do it, you can just use gzip from the terminal. So either you list the actual name or you just go compress or gzip anything, which is the asterisk, that ends in a NII. If you launch this command, you will see that now you have a NII.gz in place of the NII. Maybe I should make this larger just so that it's easier to see. All right, now we have a zipped version of that. We can also rename it so to rename things in the terminal, you use mv. It's called epd whatever .nii.gz. Let's call it, so to change the name is mv input output, so old name, new name. So mv, I gave it the old name, and now just call it diffusion.nii.gz. Okay. It's important that you also take a look at the bval file. The bval file is going to tell you the b values, so the degree of diffusion weighting for each of the volumes. In this case, we have 3 volumes, as we saw before. So I'm expecting 3 values, and probably it's going to be 0, 500, 1000, I'm expecting. You can open the bval file just with text edit, and you see it is actually 0, 500, 1000. The bvec file, we don't need it right now. It's gonna tell you some information about the direction of the gradients. It's more important for DTI. I don't even know if it's reliable for diffusion, right? Like the type of diffusion that we acquired here, or like more than the type of diffusion, the way that the files were exported from the scanner. So we have the bval, so we know we have 0, 500, 1000 within this diffusion file. So let's open FSL eyes. So we said we need FSL to do a couple of things. Actually, let's open another terminal that I use to open FSL. FSL eyes is the nifty viewer that comes with FSL. So FSL can help you to do some operations in the terminal with the files, but it also has a nifty viewer that is called FSL eyes. So I'm launching FSL eyes, and let me drag it in this specific screen. Now that we have FSL eyes, you can drag and drop the diffusion just to show. So this is the B0, so purely diffusion weighted, B value 0. And then volume, you can scroll X, Y, Z dimensions here, and this is the Z dimension. So you can scroll volume 0, volume 1. Let's correct the windowing a little bit. Okay. So volume 1, you can see, I said it before, it was pretty obvious. You can see it's a B500 because the ventricles look like this. Because it does have diffusion weighting, but it still has a lot of purity tool weighting. So it's something in between. And then the B1000 doesn't have a CSF, doesn't have bright CSF. So you could use all 3 to fit the ADC, but truthfully, what it's been done most of the time is just to use B0, B1000 and just call it a day. So for consistency and for simplicity, because if we used both 3 values to fit the exponential, it would be much more complex to do. So let's just use 0 and 1000, which is usually acknowledged as acceptable. So for this passage, we have to use a function that is called FSL, which is built in FSL. So if you install the FSL, you have this. It's called FSL ROI. The way it works, so all FSL built-in tools like FSL, Flirt, whatever, if you just type the tool name and you press enter, it's going to show you the usage. So in this case, we need this particular way of using it where you have FSL ROI, input output, T-mean, T-size. So T-mean is the 4th dimension, the first index of the 4th dimension that we're going to use, and then the size is how many we want. So if we want the B0, what we do is FSL ROI, diffusion, we call it B0.nii.gz because we have to do input output, and then T-mean is 0, and then size is 1. It means let's start from volume 0, which is the B0, for a step size of 1. So just grab the first volume whose index is 0. So we do this, and now we should have a clean B0. If you notice, yes, we do. If you notice, I'm using ITK snap for simplicity, but if I have multi-dimensional like 4D files, I use FSL, which is a bit better in that case. Anyways, so we have a B0, and then the same way we can get a B1000. So to get a B1000 trace, we do FSL ROI, diffusion B1000, but now this time we don't start from 0. We don't start from 1 because that's B500. We start from 2. In case your data set doesn't have three b-values, doesn't have, when you open the b-val, doesn't have 0, 500, 1000. In case it only has 0, 1000, you will open it, you will see it has two volumes, it doesn't have three. So in this case, instead of 2, 1, you would do 1, 1. So start from 1, be 1000, and step size of 1. In this case, we have also the be 500 in the middle. I want to skip that. So I'm doing diffusion, be 1000, start from 2 in the t dimension, and stop after a step size of 1. After we do this, you'll see, let me just use FSL for simplicity. You'll see that we have a B0. Okay, let me match the windowing. So you see the B0 is the exact same as the volume 0 of diffusion. And then let's check volume 2, which is the B1000. 0, 1000. Let's do this. 0. So you see that B1000 that we generated is the same as the third volume of diffusion. So now we have B0, B1000. I think it's a good idea when you generate all of this stuff to move it out of the DICOM folder. So I have it all here. We actually, as you know, like in our lab, we have a dedicated Nifty native folder with all the Nifties, but general, I don't care right now. I'm just putting everything here. So now we have to do a mathematical operation to use B0, B1000 to fit the exponential and get the ADC map. The ADC is the exponential coefficient, exponential term of the exponential decay function that uses the signal at B1000 and B0. Again, if you just have 2 points, you don't need to actually fit an exponential that you would have to do if you had multiple b-values. But if you only have 2 points, you can just use a simplified formula. I don't want to remember it every time, so or like recalculate it every time, so I just Google it, ADC, MRI formula, whatever. You find it, it's ADC equals minus natural logarithm of signal, which is the B1000, divided by S naught, which is the B0, divided by B, which in this case is 1000 as a number. So to put this in practice, so we change the location of the file, so we have to re-CD where the files are. So make sure that you CD, and if you do ls, you see all the stuff that you just generated. Yeah, I think. Oh yeah, okay. So you have all the files that we just generated, B0, B1000, okay? Now we can use FSL maths. FSL maths is another built-in FSL function. If you type it in and you click enter, it gives you the usage. So all of the mathematical operations you can do. In this case, we have to, let's refer to this equation, right? So FSL maths, we definitely have to do S divided by S naught. So that would be B1000 divided in FSL maths, the operation for division is dash div divided by B0. Okay, so now we have this ratio. At this point, the next thing that we do is have to do a logarithmic transformation, which in think of FSL maths as FSL maths as it's doing the operations as you are adding them. It doesn't care about whether certain operations in mathematics should have precedence. It's only going to execute one after another in the order that you give it. So it's taking this and dividing by S naught. Now we have to do a log transform. Natural logarithm in FSL, it's dot dash log. It's not going to be a base 10 log. It's a natural logarithm, same as Python. So now we have this term, ln s divided by s naught. Then we can let's say we want to put the minus sign that we haven't put yet. So let's multiply by -1. It's just as putting a minus sign. And then we have to grab this whole thing that we created and divide by b. Divide by 1000. Now, if we do it like this, it's gonna come out in squared meters divided by seconds. We want it in, so I'm messing up the units, I think. 10 to the minus, yeah, sorry, no, it's gonna take, yeah, I forget the units, I have to look it up. But long story short, we want to divide by 1 million because, yeah, I think, no, so, okay, I'll take it back. If we run the command as it is, it's gonna come out as squared millimeters divided by seconds in units. We want it to be in units 10 to the -6 millimeters squared divided by seconds. So we have to multiply by 1 million. Now we're dividing by 1000, multiplying by 1 million. You can also multiply by 1000, which is the same thing. Remember to name the output. The output is adc.nii.gz. So now we have an ADC that we generated, and it looks pretty good. How to check that the ADC looks correct from a numeric standpoint? So first of all, 0, 3000. The ventricles, so the CSF should be around 3000. You see it's 3200, 2900, so it looks correct. And the healthy white matter should be around 600, 700. It's a bit, well, sorry, we have partial volumes there. Like 900, it's a bit higher than I was expecting, but it depends on the brain and the person, I guess. What about here? 800, something more reasonable. Okay. So this looks right. So this is the ADC that you can actually use for further analysis.